Okay, it's 1:35, so we'll get started. First off, I assigned a homework, so you should be able to A, see the papers that I uploaded to Box, and B, start to be thinking about what paper you're going to write about for homework number 3. Now, I gave you a good choice of papers that I like, that I think have relevance to this class, but if you're not interested in one of those papers, it's fine to select your own. That's no problem. But again, we want to stick to the theme of polymers and composites, their basic properties, and how their basic properties relate to additive manufacturing. And so whether you're more on the material side or you're more on the additive manufacturing side, hopefully there's something in there for you to take a look at. But if you can't access the box, or if you're having problems figuring out what to do for homework number 3, I'll take questions right now if anyone wants to chime in, or you can send me an email, whatever's convenient for you, and of course, office hours, et cetera, et cetera. So we'll start off with any questions on the homework or any questions at all in this semester. No questions? All right, so again, you're welcome to chime in anytime, but you should now, after the first few weeks of the course, start to be getting an idea of the general areas that we're going to talk about. So we've spoken a lot about melt processing. We've spoken about the details of polymers and their thermal transitions so far, although we're going to get into other polymer phenomenon as the course goes on. We've talked about some details of additive, and we're going to walk through the different types of additive processes from the ASTM chart. So if we haven't covered your favorite additive process yet, just hang on. Or if there's a specific additive process that you're interested in, please let me know. I'll make sure to cover it. Or if there's a specific material or a specific application that you're interested in, we can try and squeeze it in. But the course will follow this general guideline of talking about materials and how the materials are working, some things about material properties, but then the most important aspects of the material that will lead to being able to use it in an additive process. So whether that's photopolymerization or whether that's melt rheology. Of course, we've been talking a lot about melt processing, but we'll move on. And so if you're not getting the information that's interesting to you, or you're not getting information that's useful in this course, just please give me a heads up and we can tweak it as we go on. So any questions in terms of polymers or composites or melt processing? We have about 2 or 3 more lectures on that, and then we'll start on stereolithography maybe late next week. We might need 4 lectures to finish melt processing, but it depends. But then we'll move on to photopolymerization and stereolithography after we wind up melt processing. So any questions, anything people want to chime in about?
I guess I have a question for last class. So when you were talking about the peaks, are those semi-crystalline?
That is a very good question. So let me go to the slides. Let me share my screen here. Okay, so when we were talking about the peak family, which is right on this slide right here, and all the associated peaks. So peaks in general are semi-crystalline. So they have both a TG, and any polymer that has a published TM is automatically going to be semi-crystalline. But in some cases, like with this polyphenol sulfone, this one is amorphous, so it will only have a TG. So you can look up all the properties of polyphenol sulfone, and you'll only see TG. Same thing for polyether sulfone or polycarbonate. which we also talked about, which is on, I can't remember where polycarbonate is, but, oh, yeah, right here. Polycarbonate, polysulfone, and polyether sulfone. These will all be amorphous. Meaning they only have a TG. Something like PET, which we didn't talk about necessarily. I don't know if we have it in this list. Now we don't have PET in this list either, but PET is semicrystalline. So polyethylene terephthalate will have a published TG and a published TM. And so all of these peaks, because they all have TMs, are all semicrystalline. So that's, if you're unsure as to whether a polymer is amorphous and just glassy or semicrystalline, where it has both an amorphous and a crystalline phase, if you look at its thermal transitions, you can tell right away, because for amorphous polymers, you won't have a TM. Or you can put it in the DSC and you can see, okay, there's only glass transition temperature, there's no melting or crystallization peak. And so that's, if you're unsure as to whether a polymer is semicrystalline or not, those are some guideposts to tell you what's going on. Does that work?
Yeah, that makes sense. Thanks a lot.
Great. Yeah. Sometimes it's left unsaid. Sometimes, if you get a funny polymer, there will be some misinformation. So people like to say that PVC is semicrystalline, and it's not. There is no TM for PVC in the polymer handbook, and so you need to look at some of these materials with a critical eye.
Okay, yeah, I think now it makes sense, like what you're saying about looking at the TG and TM.
Great. Good question. Any other questions? All right, so I have this set of slides up because we're going to talk about the details of composites. We've talked a lot about the details of polymers. And of course, generally, composites are just two different materials that are put together in order to get some new set of properties. And generally, we make composite materials to get this composite effect, or to get properties that you can't get with just a pure material. And there's composite metals, although alloys are not really composites, they're just a different type of metal. But there's composites that we make with metals. There's, of course, composites that we make with ceramics. And there's lots of composites that we make with polymers, because most polymers will have colorant, fillers, additives. And so whether it's a mechanical a filler that has to do with mechanical properties, like this is looking at the fracture toughness of epoxy resins filled with alumina, whether it's for mechanical purposes or some other purpose, most polymers are used as composites. And so we really need to get we really need to get oriented with why composites are important, and then how some composites process differently than the pure polymer phase. And so there's lots of general information out there in the literature on this composite effect, where you get higher fracture toughness from the mixture versus either of the pure components. And we talked about that last time, but I just wanted to remind you why composites are important. And now we're going to talk about the details of what composites are, and then we'll talk about how to additive composites. So I think we left off on this slide. This is in lecture 3.5, and we left off on this slide last time talking about what a composite looks like from sort of a microscopic viewpoint. And the key part about this whole section of slides, lecture 3.5 today, is making this interface, or making the interface between the filler and the polymer. So if you have a poorly formed interface and you don't have any adhesion between your filler and your matrix, in general, you're going to have a not very good composite. And so a lot of composite science relies on how do you get good adhesion or compatibilization or good mixing. And so when you read the composite literature, you hear about phenomena such as adhesion, compatibilization, dispersion, etc. Because when you're mixing two materials together, those are the things that you have to worry about. If you can imagine like a fiberglass sailboat, if the glass fibers didn't stick to the vinyl ester or epoxy resin that you use, it would not be as tough of a material because you don't get that reinforcing effect. Or in lots of instances, if you don't have a good interphase, you can't get this composite effect that we just spoke about. So I have a few slides here talking about what that interface is and some things that you should be aware of as you start to specify a composite. And there's lots of strategies out there to work on the interface or to modify the interface. And I just want to give you a preview of what people do so you know a good composite when you see one. Or you can think about some of these factors if you're designing a material or a part that's a composite. So fiberglass composites, you know, usually we just call them fiberglass, but these are glass fibers mixed with either a thermoplastic or a thermosetting polymer. So we can have thermoset, or you know that thermosets are the same as crosslink polymers. And there's also a category of thermoplastic composites. And you notice that thermoplastic or thermosetting or crosslink composites are named for the polymer matrix that's in there. And so sometimes when we call it a fiberglass composite, or sometimes when it's called a carbon fiber composite, you don't really know the polymer that's in there unless it's specified. But in order to make a fiberglass composite, so you make glass fibers, and then what you do is this process called sizing. So sizing is an old word from fiber technology, but it basically means surface coating or surface functionalization. So these glass fibers are going to look like, you know, fiberglass, if you want fiberglass insulation, or woven mats. We looked at a carbon fiber mat when we introduced this topic, but all of these materials have a surface coating applied to them that's usually done when they're made. So these are there are all sorts of different types of glass fibers made or carbon fibers made, and they come with all different sorts of surface coatings. So you can look up in material supply catalogs or in various tables of different fibers and fiber types that are available. It will often say what surface coating it is, because you'll see that the surface coating has to relate to whatever matrix you're going to use. And so the key to this interphase region is you need one part of the interphase to stick to the fiber or the filler, and you need the other part of the interphase to stick to the matrix. And so if you want, this is like a surfactant or compatibilizer between the two phases, and we'll talk about some of that chemistry. But this is, in general, what fiberglass processing might look like. And of course, you can take these fibers once they're sized and you can weave them into a mat, or you can chop them up, etc. But this important aspect of sizing, and you have to match the type of sizing to the type of matrix you're going to use, is important. And so if you look into the fiberglass or glass composite literature, you see lots of things that are e-glass composites. Sometimes you see C-glass. There's a lot of different glasses though. R-glass, every once in a while you see. But if you want to go make a fishing boat, you'll generally buy an e-glass composite, or you'll buy an e-glass kit, or you'll buy e-glass fibers, and those fibers will be sized for a vinyl ester resin or an epoxy resin, depending on what matrix you're going to use. And so this is just some nomenclature that you should know if you go out and try and find different glass fibers. And this is just from the glass industry. This is how they specify it. And so what's different about all these glasses is the chemical composition. And so if you're interested in glass, we have some glass science classes at Penn State, but this is to give you a guideline as to sort of what all the different types of glasses are when you look them up in the catalog. What's important is to think about what the fiber type is. So whether it's E-glass or S-glass, these are carbon fibers. But recently, there's been a lot of work on Kevlar fiber composites, which are called aramids. So Kevlar is a brand name of a specific polymer, and aramid is the generic name of the class of that polymer. And there are these new fibers called spectra fibers, which is ultra high molecular weight polyethylene. So this is the same polyethylene that's in a milk jug. However, it's very, very high molecular weight, and it's pulled into a very strong fiber. And you can see that these polyethylene fibers are on the order of the same Young's modulus as Kevlar and are higher strength than glass fibers. Of course, carbon fibers still rule in terms of Young's modulus, and they mostly rule in terms of strength. They're also very light, but some of these polymer fibers like Kevlar fibers or spectra fibers are starting to compete with the high-end carbon fibers. So you see all these different properties here. You see upper use temperature. That's where some of the polymers fall short compared to glass versus carbon. But now this gives you an idea of, okay, I want these sort of properties for my filler, and this, high strength, moderate strength, what's the use temperature going to be? But now how do I get these fibers in a place where I can use them with whatever matrix I'm interested in, whether it's a thermosetting matrix or a thermoplastic matrix? So remember, sizing systems is basically sizing is coding. Of the fibers. And so we want to enhance fiber matrix adhesion. That's really important, especially in the final product. We want to improve the mechanical properties at the interphase region. That's important. This is interesting. Optimize fiber wetting during pre-pregging or molding operations. So this is during processing. You need to have good wetting, and that goes along with good dispersion. So let's look back at the twin screw extruder. So we're all on the same page with how these composites are made. So this is back in lecture 3. Let's see if it comes up quickly here. So we have this twin screw extruder where we mix melted polymer and filler together. And there's lots of shear, there's lots of mixing going on here. But if dispersion is not favored, if we don't get good wetting, generally we'll get clumps of filler and clumps of polymer, and that just doesn't make a very good composite. We mostly want composites that have good dispersion of filler in matrix. And so that means good wetting, that means good sizing. In order to get something to mix well, you need to have good interfacial compatibilization between the two phases. If they don't mix, you're going to wind up with clumps of stuff, and that just doesn't make a very good material. And so composites are not only designed for dispersion in the end product, but in order to get these things processed correctly, you also need to have good dispersion. And so that's generally done in what we might call a composite master batch. And then we take that and we do additive from that feedstock. So in general, we're not going to make a composite material as we're doing the additive process. So we don't have one of these dual feed extruders hooked up to our additive process. In general, we're going to make a composite first, or we're going to compound the composite as our feedstock, and then we're going to go to the additive process after that. Oh, I see a chat here. What does the ratio of polymer to other material need to be for a composite? So it depends. So the question is, everyone can see this chat if you bring up your chat, I think. But Paula asks, what does the ratio of polymer to other material need to be for a composite? Is it 50-50, or does it depend on the type of composite? So it depends on the type of composite, and it depends on the properties you want. Like in this case, this maximum occurs at a 20 volume percent particle to polymer. So this composite is 20% volume percent filler and 80 volume percent polymer. In a fiberglass composite, it might be 40% filler and 60% glass. Or in another composite, it might only be 5% chopped carbon fiber and 95% polymer. So in a lot of cases, it depends on the composite design, and it depends on what properties people are looking for. And the cool thing about composite materials is you could have a 5%. If you want this fracture toughness, you could have a 10%. If you want this fracture toughness, you could have 20. If you want to add more cheap alumina trihydrate and less epoxy, you could go a little bit higher, but you're going to suffer in properties. So you can get all kinds of different properties from just two materials. And so we'll leave the volume fraction open in this discussion, or general, and that's a variable that you get to dial in depending on what your interests are. So if that works, we can go on. Otherwise, I can answer any more questions people have about details of composites.
That makes sense. Thanks.
Great. Okay, so hopefully you're getting the feeling for some of the issues around composites, what composites are, how they relate to thermoplastics and thermosets. But it's not only you need good composite wetting or good sizing in the final part, you also need it during processing to make dispersion of that material easier. And then this is just another sort of aside. The fibers are often very small and thin, and so having a sizing on them protects them during storage and things like that. So this is a really interesting part of composite science, and unless you've taken a composites course, which is basically all about interfacial design, You know, you might not be aware of that a carbon fiber composite has lots of things going on, especially at that interface. So in order to make sense of this idea of you have to connect a filler to a matrix, what we use for glass or silica fillers and polymers is this thing called silane coupling agents. And so silane is the type of chemistry that we're going to use. So this is a trimethoxy silane. Whoops. And so that silicon OCH3 and then 3 of those, that's called a trimethoxysilane, and this reacts with glass. And glass, of course, is just another name for silica. And so the silanol groups, or the SiOH groups on glass surfaces and silica surfaces react with this trimethoxysilane. And then you have this organic part. So the carbon reacts with the polymer. And so depending on the polymer type, whether it's a vinyl polymer like polyethylene or PVC, or whether it's an epoxy, or whether it's like a rubber where you might want to do some mercapto cross-linking, or a styrene group, et cetera, you have all different choices of polymer chemistry that you need to match with whatever polymer matrix you're interested in. So for glass composites, of course, glass has very much the same. This is a triethoxy silane. Similar function as trimethoxysilanes, just a little bit slower reacting because it's an ethoxy or 2 carbons versus a methoxy, which is 1. But anyway, all of these silane coupling agents have one side of the molecule that reacts with glass and the other side that reacts with whatever polymer you want. So if you're going to make your sailboat out of an epoxy resin, you use this epoxy silane coupling agent on your glass. If you're going to do a vinyl ester, you probably want something like that cationic styryl or a cationic methacrylate to react with your vinyl ester resin. And so this is important, and this is right at the surface of the glass fiber. So if we look here, you take the glass fiber with silanols on it. And you take your silane coupling agent. So this is just an organic chemistry nomenclature for R is something organic that reacts with a polymer. So here's your silane coupling agent. And then now you're going to have a glass fiber surface that's modified for adhesion with the polymer. And again, if you know you're going to use glass as your filler, you want to tune your silane coupling agent chemistry to whatever polymer you're going to use. And so this is how this looks in a schematic form. So you have a glass fiber. This is your amine-based silane coupling agent. So you look in your silane coupling agent table. And so this is primary amine right here. you're going to use that silane coupling agent to modify the glass surface. And it turns out that primary amines react with epoxies. If I can get this to go off. So this is an epoxide or epoxy ring. And the way that epoxy works, that they're amine cures, is this amine attacks the carbon on the ring and opens it up. And now you get a bond between this squiggle is the polymer. And of course, you're going to have epoxies, more epoxy reactions in your epoxy resin. And so you have polymer chains, you have your glass fiber, and now this silane coupling agent is the interface between the two. So this is a diagram of what the chemistry looks like when you put together the fiber, the silane coupling agent, and then customize that silane coupling agent for what's happening with your polymer chemistry. And so this isn't a polymer chemistry class. We're not going to do lots of chemistry, but this is your sort of FYI about tuning the silane coupling agent to the polymer chemistry that you're going to use. Because if it's not an amine, if you use something that doesn't react with an epoxy, then your silane coupling agent is not going to be as effective as something like this, where you get this covalent bond that does your interfacial adhesion. So I'll pause here for a second. If there are any questions, you can put them in the chat, or you can unmute yourself and just go ahead and ask. But this is important to start thinking about: what are composites like from a molecular viewpoint? How do you design a composite, or at least how do you choose the right components of a composite in order to get whatever composite effect or material properties that you're interested in? So any questions?
Yeah, I have a question.
Go ahead.
So can you actually fine tune the final property of the composite by like tuning the amount of coupling agent that you use? Like if you use less coupling agent, is it gonna make the material like softer, or is it just gonna make it like worse?
Yeah, in general, you want your filler to be as coated in coupling agent as you can. So you generally don't say, well, I'm going to do only 20% coupling agent or 80% coupling agent. You tend to adjust the properties of the composite by adjusting the filler matrix ratio, or by adjusting the filler type or matrix type. And so usually when you design a composite, you want as good a compatibilization between the two phases as you can get, which means 100% coverage or optimized coverage of coupling agent. And then you tweak the properties of the composite by the filler matrix ratio, or by the choice of maybe a polymer that has a little bit lower modulus or a different type of fiber. And so that's really your design space. There isn't a lot of like, let's try 50% filler, let's try 70%, or let's try 50% coupling agent or 70% coupling agent. That's not really how this is done, because in order to get the best composite properties, you want as good as possible adhesion.
Okay. All right. Thank you.
Yep. And you want as good as possible dispersion as well. So you want to maximize this, and then you go and tweak the other parameters that you are interested in. But that's a good question. Any other questions? All right, we'll keep going on composites. This is just another FYI that maleic anhydride, you often see maleic anhydride modified polypropylene, because the one thing about polypropylene or polyolefins in general is polyolefins are nonpolar. And so polyethylene and polypropylene are all just carbon, hydrogen, aliphatic polymers, which means they don't stick to anything because they're very nonpolar. So if you know what wax is, which is just short chain saturated alkanes, or grease or something like that, it doesn't stick to anything. And so oftentimes you need some polarity, and polarity is basically you need some polarized bonds, you need some oxygen in there, you need some OHs. In this case, we're going to use maleic anhydride, which is just the name of this fancy thing. But this introduces maleic anhydride, introduces polarity to help polypropylene bond to other things, like fillers. So if you try and make a polypropylene composite out of just pure polypropylene, it's really hard to get anything to mix in there. And so that's why when you go to ExxonMobil and say, I'm going to make a polypropylene composite, but I need 5% maleic anhydride in polypropylene, they sell that polymer specifically to make polypropylene composites and get this good dispersion or get these interactions between the polymer chain and the filler. Because most fillers are a little bit polar, like glass. Glass has silanol groups on the surface, or carbon fiber will often have a little oxygen on the surface. And so for polymers that aren't very polar, you need to add some polarity back in. So you might see when you're looking up different grades of polypropylene, maleic anhydride modified polypropylene or something like that. And so this is just a FYI as to what that is. And so once you have this maleic anhydride modified polypropylene, so this is maleic anhydride modified PP, it turns out that amines that we looked at before really like maleic anhydride. And then this compatibilization happens during extrusion. So reaction during extrusion helps form well-dispersed master batch. And so oftentimes you hear reactive extrusion. This is one form of what that is. And so again, you're just making now a covalent bond between your matrix, which in our case is going to always be the polymer, and your filler. And remember, this doesn't have to be a glass fiber. This could be particle, chop fiber, etc. If we're going to extrude it, it's probably not a continuous fiber because we'll just cut up that fiber in the extruder. But this sort of sizing technology works on lots of different types of fillers that are all silica based because, of course, we use a silane to connect to silica. Any questions on glass or on this idea of silane coupling agents?
I have a quick question just on the mechanism that's like being shown right now.
Sure.
So it looks like in this reaction, you're just kicking off like a water molecule. Is that like being evaporated off, or what's happening there? Or is that just like getting stuck in the matrix?
No, that's a very good question. And so, yes, this is a dehydration reaction. Of course, this is not very mechanistic. This is just showing the products and the reactants. And so there's things that happen in order to get that dehydration to happen. But you're right, you subtract H2O out of this, and water in polymers is usually bad because it degrades their properties. And if this is under high temperature, of course, water at high temperature is going to be a gas. And so you get some foaming and some real problems during extrusion if you have too much water in the polymer. And we talked about drying polymers or drying feedstocks before you go to extrusion. And so what often happens in some of these extruders is that there's a vacuum pulled on part of the barrel in order to degas the polymer, or there's a degassing system in the extruder where you can vent the water that comes out. And so that gets into the nitty-gritty of how do you design a compounding extruder, or how do you get these side products out of the reaction. But that's how this is handled. So there can be a significant amount of water that comes off in this reaction due to how much filler and how much maleic anhydride that you have in the system. But some of the extruder technology can handle that. Of course, costs money, it adds difficulty, but being able to degas polymers inside the extruder or dehydrate polymers inside the extruder is something that compounding extruders can be designed for. Other questions?
Yeah, I have one. It's linked to the same question as before with the water. Would a reaction or a extruder nozzle usually get above 100 degrees C where it would just evaporate off, or is it a lot more complex than that?
So usually, if we go back to a compounding extruder, let me find it right here. So if we go back to our picture of a compounding extruder, if the gas is coming out here, that can be a problem. Or if the water is coming out at the end, we can get foaming of that feedstock, which isn't good. And so in general, extruders will be at 250 degrees Celsius or 300 degrees Celsius, because if you look at all the polymers that we've discussed so far, their TGs and TMs are high. They're above 100 C. And so the water is definitely going to want to evaporate or boil or come out of the polymer as soon as it's made. And so what happens, and it isn't shown in this schematic necessarily, is that there will be a vacuum line here, or there will be a degassing section. I wonder if it's shown in here. Oh, I can get off of this. Yeah, open degassing. So I knew there would be something like that. So depending on, you see that now this is a very fancy extruder because there's a sort of screw part, and then there's a rotor part, which is there's less shear in here, and it also controls the flow as well. But then you might have a degassing section. You might have a section that you're pulling vacuum on, because you can still pull gas out of a polymer, but if the openings are small enough, the polymer has enough surface tension and high enough viscosity that it won't go up in that degassed port. And so there's lots of sort of extruder design technology to deal with that before you get to the opening, where you either do molding or you do extrusion of a filament or something like that. because you really don't want any water to be coming out there because it's going to be foaming. It's going to cause really bad part quality. And that's oftentimes why we dry polymers before they're extruded, because lots of extruders don't have degassing ports on them. It's expensive. It's another thing you have to worry about. Compounding extruders generally do have degassing on them, but that's because we know that there's going to be water formed in some of the reactions. Of course, fillers carry water in too, and so you really want to try and take care of that water before it gets out and through the extruder, because it'll cause all sorts of problems in your product. Whereas if you design your machine to handle that, it should be fine. And sometimes you walk up to an extruder, if you've ever taken a plant tour of a plastics factory or an injection molding factory or something like that, you could say, hey, does this extruder have a degassing port on it or not? And the operator will say, oh yeah, we degas stuff on this, or no, this is just your run-of-the-mill extruder. And so it's just part of the technology of extrusion that if you start to deal in a lot of extrusion, you'll get familiar with. Does that address degassing, formation of water, things like that? Is that good enough?
Yeah, it does. Makes perfect sense.
Yeah, and like we've shown before, I mean, I'm going to try not to show all the YouTube videos in this class, but if you're curious about some of this stuff, there are some really awesome YouTube videos on extrusion, blow molding. If you want to see how laundry detergent bottles are made or shampoo bottles. I have to say, being a polymer person, the YouTube videos are pretty awesome, not to mention all the awesome additive manufacturing videos online. So if you want to see what a degassing extruder looks like, you could just dial it up on YouTube and you'll be able to find a bunch of videos. Okay, good questions. Any others? All right. Back to fibers and the details of fibers. So that's pretty much the story of glass fibers. And so we might say, well, fiberglass is outdated. I don't use a lot of fiberglass, but there are still tons of glass composites out there because glass is cheap. Polymers are more expensive. And so people would really like to fill polymers with glass when they can. In fact, a lot of nylon is filled with glass because nylon is a polar polymer. Glass is inexpensive, and glass helps to increase the modulus of nylon, so you can use nylon as an engineering material. And most composites in automotive are still glass or clay composites. So I should write that down. Glass or clay, because the chemistry is similar for clay because it's an aluminosilicate. And so you can still use silane coupling agents and some other surfactants for clay composites. And of course, clay is really cheap. And so one of the first composites that was used widely in automotive was a clay polypropylene bumper for Toyotas. And so that's still quoted as one of the big first examples. And so Toyota came out with this plastic bumper, and it was a clay polypropylene composite that they designed. So this is the story of glass and polymers. Now we're going to talk about carbon fibers, and you'll notice that it's a very similar story, although there are some details of carbon fibers, like how they're made, which is pretty cool. So if you want to look up how carbon fibers are made, there are these polyacrylonitrile or pan-based fibers. And so this is an acrylonitrile monomer. This is polyacrylonitrile, which is a polymer. And you take that polymer and pyrolyze it, and you get eventually to carbon fibers. And so the best carbon fibers, or the highest strength carbon fibers, are made out of this polyacrylonitrile process. And so when we'll look at tables of carbon fibers, you'll see pan-based fibers and pitch-based fibers, and they're different, and I'll describe the differences. So here's the carbonization to form carbon fibers. And so you take a nice polymer, and then you burn it up, and eventually you form all of these graphitic rings, And of course, that's what carbon fibers are, oriented graphite fibers. This is what the process looks like. So you have a polyacrylonitrile fiber supply. You have oxidized fibers. So this is pan fiber supply. So you have to make polyacrylonitrile fibers first, and you can look up how that's done if you're interested in that. But then you have carbonization, graphitization. You often do an electrostatic surface treatment, and then sizing. You know that any good fiber is going to be sized. And so the electrolytic oxidation introduces some oxygen to graphite surfaces, because graphite is also very non-polar, so maybe there's a little nitrogen in there, but it's mostly carbon and some hydrogen, so not a lot of things stick to that. And so you need to do a little bit of oxidation, and then you can apply whatever sizing treatment you want before you get your carbon fiber, your bundles of carbon fiber that you can weave and things like that. So the types of treatments that people put on carbon fiber are, nitrogen functionality that might be left over from the acrylonitrile. They might do a cationic surface treatment. They might do some sort of oxidation where you wind up with acidic groups. So that's a carboxylic acid or a lactone type of group. And here's alcohol or some sort of alkoxy group. And so depending on what type of fiber you buy, depending on how you want to use that fiber, there will be some indication of surface treatment. Now, you don't use silane coupling agents on carbon fibers because there is no glass for the silane to stick to. So you remember that the silane coupling agent has the silicon trimethoxy group on it, or the silane part of the silane coupling agent. But that only works when you have silanols or when you have these glass surfaces. And so this silicon OH bond is different than these carbon oxygen species shown here. And so the chemistry of carbon fiber sizing is not the same as glass, and in some cases, we don't use the same sorts of molecules. They use these oxygenated type of species, and then you buy the carbon fiber saying it's highly oxidized carbon fiber, or it's moderately oxidized, or it's carbon fiber that's compatible with epoxy resin or something else. And so again, there's a different nomenclature and different things are going on because it's a different surface. But the idea is the same, that you buy certain carbon fibers with certain surface treatments that you can use with certain matrices. So again, we're trying to create this interphase. And so this is just an example of how it might look in terms of your concentration gradient of sizing that's close to the fiber, and then your resin. And so you make this really nice interface. And of course, the sizing agent and the resin have to be compatible in order to get good adhesion. Now, there are tons of carbon fibers out there. And so we're not going to cover all the details of different carbon fibers, but whether you buy those carbon fibers from BP Amoco or whoever they're called now, or I think Hexcel is still around. I know Toray is still around. They're a huge supplier of carbon fiber. And so they've got different densities, they've got different strengths, they've got different moduli, but all these different grades, if you look into the details of what the grade is, it will tell you about the surface treatment. Highly oxidized, nitrogen enriched, cationic surface treatment, carboxylic acid content of X, all of those different things. And so if you're interested in a deep dive on carbon fibers, there will be lots to look at, but this just gives you some sort of a checklist of what you might be interested in for designing a composite. And then just one slide on pitch-based fibers. So pitch precursors are from coal tar-derived mesophase or petroleum-derived mesophase. So this is the heaviest products from oil refining. So after you do your gasoline process or your petrochemical process and take off all the valuable light chemicals, you're left with this pitch, and you can make carbon fibers from pitch. But these pitch-based fibers have poorer properties than pan-based. Fibers, but they're a lot cheaper. You can imagine that they're cheaper because you take something that's left after you refine a barrel of oil, put it through this fiber extruder, and then go ahead and pyrolyze it. And that's a lot cheaper than making polyacrylonitrile and acid spinning it, making polyacrylonitrile fibers, et cetera, et cetera. And so pitch-based fibers are used in non-critical applications. So if you're making, let's say, a carbon fiber body panel, or if you're making a carbon fiber cover for a consumer good, or if you just want the lightness of carbon fibers and not necessarily the strength, you know, if you're going to make an airplane, all aerospace fibers are pan-based carbon fibers. But for just sort of general use application of carbon fiber where you just need low density, because carbon fibers are a lot less dense than glass fibers, you can get away with these pitch-based fibers. So that's some general guidelines on this idea of what could the fillers be? What do we need to think about in terms of sizing? And then how do you create this useful composite in order to get the composite effect that we talked about on the first slide of the lecture? So again, we're not going to go deep into different sorts of composites, but you'll encounter a lot of composites as we study them in the realm of additive. So if it's a particle-based or silica composite, or if it's a cellulose nanocrystal, or if it's a carbon fiber, chopped carbon fiber, or continuous carbon fiber composite, or chopped glass fiber, at least you'll have some things to think about in terms of what that composite is and how is it used in additive. Now, the thing you have to remember is that when you look at this, do you think the viscosity of this fiber plus matrix, or let's say filler plus matrix, is higher or lower than just the matrix itself? So you're putting solid things into a polymer, and the polymer has a certain viscosity, and we've talked about the viscosity of polymers before. Do you think the viscosity is higher or lower of a composite compared to the base polymer?
Higher.
Yes, higher, for sure. You put solid in something that's a fluid, and so that fluid is going to get more viscous. And do you think that processing a composite is easier or more difficult than processing just a base polymer, say, in an additive process?
More difficult.
That's right. Thanks, Eddie. Appreciate that. Yeah, so it's going to be harder to process composites. They're going to be more viscous. And so there's more things to think about when we start to put composites through our additive process compared to just pure polymers. So that's a really interesting thing to think about, that, okay, you know, I can process a polymer, I can do the additive, et cetera, but as soon as I want to composite, I add another level of difficulty in my additive process. So if you go back to, and let me just go back to this slide that we started on, if I want the higher fracture toughness from this composite effect, I'm going to have to pay for it in terms of processing difficulty, because it's going to be harder to process that 20 volume percent filler material than it will be to process the base epoxy resin. Whether I'm doing melt processing or stereolithography or some other process, I don't get that composite effect without some downside. And oftentimes processing the composite is the hard part. So that's something to remember. Of course, now that we're doing additive manufacturing, I may be able to design my additive process around the composite material, or I might be able to do some ink formulation for effective direct ink writing, or I can adjust my filler composition so it's reasonable to process. But that's a key part of composite design for additive manufacturing, is I just can't get whatever filler I want. I need to think about how my composite material is going to flow. What are the melt properties? Am I getting the same sorts of rheology that I need in order to make a successful additive process? Or when we talk about SLS, am I going to get good sintering in my composite material so the powder sticks together? Or if I do stereolithography, am I going to be able to get effective binding of the material? And so composite additive can be successful. I mean, there's lots of composite parts out there, like this photopolymer clay composite and this Teflon 3D resin, but I'm adding a degree of difficulty by introducing the composite into an additive process. And there will be homework on that. There will be readings that we do on that, but that's something that you want to watch out for. Not only how you design a composite in the first place, but the problems that you're going to introduce when you start to go through the additive process. Okay, so you should be oriented a little bit to polymer materials. Now you're oriented a little bit to composite materials. And we're going to keep going on details of additive processing and finish up melt or material extrusion AM processing. We're not going to be off of melt processing yet because we need to get to SLS, which we will. But I'll pause here and just ask if there are any more questions on composite materials, polymer materials. If I'm talking about polymers that you're not familiar with, or we're going too fast through the materials part, I'll just open up the floor for any questions right now. All right. So feel free to send me an email on office hours, or if you want to have an individual discussion, or if the class is resonating and you want to go deeper into something, or the class is not resonating and you want to try and steer the discussion towards your interest, just let me know. But we're going to move on to lecture 4, which should be in the box. And again, the lectures are just sequentially numbered as I come up with them. And so don't worry about what set of slides we're on. Just follow along, and they're marked and time-stamped in box. But anyway, we're going to talk, to wrap up material extrusion AM, we're going to talk in detail about filaments. Because the one cool thing about additive is you basically have these constituent units, whether it's a filament or a layer or a polymer powder, that you have to build your part out of. And so this is for material extrusion, AM. And this is different than if you make polymer parts out of injection molding, where you just injection mold or mold a cavity. You get a solid part out of that. You know, depending on how the part is designed, you might have to glue two pieces together or something like that if you can't injection mold the part all as one piece. But injection molding, even though you do polymer extrusion, you don't wind up with these roads. But when you watch a video on YouTube about MakerBot printing, or you watch that Ultimaker printing video that we covered when we were talking about the support, the entire part is made up of these filaments or strings of extruded polymer. We're going to call them roads because that's their scientific name. And so you need to figure out how to build a part out of these things. And so these roads are small. Generally, they're between 100 microns to 1 millimeter. But in large scale printing like BAM, they can be up to 1 inch. And so you get really interesting looking shapes and shapes of cars when you make the shape out of 1 inch roads. But this is sort of the constitutive unit that we have to deal with. And you notice in these roads, they're not perfectly round. That happens. And there are gaps in the middle. And this also doesn't exist in injection molding. The point of injection molding is you get the cavity completely filled, and so there's no gaps in the part. You'll also notice that between these roads, you have an interface. So you have a side interface, and of course you have a layer interface. And so when you build up a solid part out of these roads, basically your part is filled with interfaces and gaps. And that's completely different than an injection molded piece of plastic like your mouse cover or your computer case or your car bumper or any sort of conventional plastic part that you have. None of this stuff exists in an injection molded or rotomolded part or something like that. And so we need to be able to deal with this in additive manufacturing and figure out what effect do all these interfaces have, and then in some cases how to mitigate all these things, because these gaps and interfaces are also known as defects in conventional manufacturing. And so roads can have lots of defects. And that's an issue. So people have studied this, and this is a really nice paper that you can check out right here. And these are some figures from that paper. But people have studied this in terms of material extrusion AM and tried to figure out how to mitigate some of these issues. And one of the things that they've looked at is flattening the filament in order to try and do gap filling. So this delta is your offset in terms of how in terms of the difference between the layer height of the printer and the diameter of the road that you extrude. And so if you don't have a picture of what this looks like in your head, I'll bring up a picture at the start of the lecture next time. But if you've watched videos online of how material extrusion AM works, basically the printer is moving up layer by layer. So this is, well, let me draw the full arrow here. So the layer height is set by the printer control software. So that's how much the printer moves up per layer. But the road diameter is set by the die orifice size, and a little bit by the viscosity and the print speed and things that you can control. So in this type of printing, you sort of get what row diameter you get under a certain set of conditions, and then you can adjust the layer height in the software in order to get this flattening effect. And you look at the schematic right here, and let me change pen colors so you can actually see it. So this is a flattened oval road that came out as circular, and then this is the gap. And this is a cross section of a printed part. And so here are the layers. So there are the layers. So you can see how this part is built up of these rows. And so that's really interesting, because when you look at an additively manufactured part, you say, well, it's got some ridges on the surface, but it looks like a solid piece of plastic. And it's certainly not a solid piece of plastic inside. You'll talk about infill design and other things you can do with additively manufactured parts in terms of design and shape in some of your other classes. But this is now a materials issue, because if you're going to do material extrusion additive manufacturing using polymers or composites, you're going to have to deal with this. So any questions on that, or any details? Like I said, I'll bring up a schematic so you can get oriented to exactly what we're talking about in terms of the material extrusion AM process if you haven't studied it. But is anyone lost on sort of the physical picture here, or the physical situation?
Dr. Hickner?
Yeah.
I just put it in the chat, but I can just say it. So is the flattening effect from, I guess, the weight of the polymer, or is it kind of from something else?
Oh, sorry, Eddie, I wasn't looking at the chat. I see it now. So the flattening is a little due to gravity, but mostly it's due to how the printer is set up in terms of the layer height. So flattening, so we can have a little flattening due to polymer slumping. With gravity. But mostly it's due to flattening is controlled by printer layer height setting. And so basically the nozzle of the printer is pushing down on that road as it extrudes it a little bit, and you get this flattening or this oblong shape, because the nozzle is usually a circle, and so you should extrude a pure cylinder, but the flattening occurs because of the mechanics of the printer, and I'll show a detailed picture of that next time so we're all oriented. Good question. And any other questions on the physical situation?
So I have a question. Pretty much you're saying that the distance between the nozzle and the layer height is very short, and that's why it's kind of like making it a flat surface? Or I guess I just don't understand why is the layer height influencing like the fact of it becoming flat?
Yeah, so the layer height is a setting
No,
In-
I understand what the layer height is. I guess like my question is the distance between the nozzle and the layer height very, very small?
Yes. Yeah. So if you make the layer height, so if you think about it from a fun or a theoretical point of view, if you extrude a perfect cylinder and you set the layer height to the exact diameter of that cylinder, there won't be any mechanical flattening, or the printer won't be pushing down on that cylinder, and you'll just get a very little slumping. But if the layer height is less than the cylinder diameter, the cylinder is extruded out into a smaller gap, and that causes flattening. And so we'll talk about that next time, and that's where we'll start. But basically, instead of this perfect cylinder that comes out, the layer height, or the layer, you're extruding a road into a small gap between a part that's already built and the next layer you're going to put on it. And so depending on how much space you give the road to extrude into, you can have more or less flattening. And we're out of time, but let me show the picture. Let me see if I can just find the picture right here.
And also, I guess like additional to that, also having the distance very far apart could, instead of like just benefiting it to make that perfect cylinder, it would be also a bad thing, right? If the layer height was like very, I guess the distance between the layer height and the nozzle was very separated.
Yeah, if the layer height is too high, you won't get any compression, and you won't get any adhesion between the different layers. And so let me see if I can find my filament picture. Right here. So the this is the nozzle, the heated liquefier. And so this gap is where you extrude the road coming out of this. So this is going to be the road into this gap, which is the layer height. So you're right. If you're too far away, if the layer height is too big, you extrude a road and you don't get very good adhesion to the next layer. But you try and make this gap a little bit smaller to get some flattening right at this interface. And so we'll pick this up next time, but this is critical because when you're building a part out of all these different fibers, you need to get the geometry of those fibers and how they're laid together just right, which is usually the printer takes care of it. But if you start to have defects like you're not getting good fusion between roads, that's all in the printer settings. And so you need to be able to inspect the part and to figure out what defects you might be getting. So we'll close here for now. Again, I'll open up the floor for questions, but we'll pick this up next time and describe in detail how these types of defects relate to polymers, composites, what might be going on in our finished parts. Any questions? Any more questions that people want to talk about before we sign off for today? Okay, well, my suggestion is to remind yourself what material extrusion AM looks like. Take a look at a couple of videos. I'll find a nice video and a nice schematic to start us off for class on Thursday. So thank you very much. I will see you on Zoom on Thursday. Bye-bye.
Thank you.
Thank you.